All right, so in the last video we talked about the graphic equalizer and how it was basically just the summation of a bunch of FIR filters that were low pass, band pass, or high pass filters. Now we're going to talk about the next application, which is the notch filter. So if you remember from Project 2, when we did the WinDSK demonstration, the notch filter basically attenuates a specific frequency to 0 while leaving the surrounding frequencies relatively unattenuated. Of course, the notch filter is not perfect, so frequencies that are still near the notch frequency will get attenuated still. So just like before in our design, we're going to start in MATLAB, and then we're going to take those, we're going to generate the coefficients in MATLAB, and then we're going to use the script and convert those coefficients into a C file, and then use them as the coefficients in our program in C, and then download it to the DSP board. So here we got the code for the notch filter. So just like with all the other filters, you have to select the sampling frequency. Just like before, I'm going to set the sampling frequency to 8 kilohertz because I'm going to be using audible frequencies, and I don't want to use frequencies that are too high pitched because they tend to be irritating. So I've left the sampling frequency at 8,000, but you can easily just apply the same thing for the higher sampling frequency filters. And again, the added benefit of using the lowest sampling frequency filter is that I get the ability to use the most taps, so my filter looks the smoothest. So right now I set my notch frequency to 500 hertz. And so just like before, the number of taps is controlled by the sampling frequency. Again, these numbers are slightly less than, if I go over here to the coefficient generator, these are the maximum amount, but the number of taps I've chosen is slightly less than the maximum amount, just to be on the safe side, even though I've tested for the maximum values, but they're based on the observations we observed in Project 2. So the main thing about the notch filter is that the transfer function for the notch filter at this stage is unknown. Of course, we'll talk about the transfer function of the notch filter in a later project, but for now, we don't know what the transfer function of the notch filter is. Luckily, FIR filter design doesn't require us to know the transfer function of the notch filter. Instead, all we need to do is shape the frequency response to look like a notch filter, how we want the notch filter to look like. So I've shaped my frequency response using this. So this is an exponential. So it's 1 minus the exponential of the negative absolute value based on how far the frequency is from the notch divided by 100. So if I run this code, so I can observe some of the results. All right. So this is what the shaped notch filter looks like. At the notch frequency at 500, it goes down to 0, and then it uses the exponential to create this curved shape. This is what we're going to use as our notch filter. So notice that if your frequency is still near the notch frequency of 500, you're still going to get attenuated. But as you get farther away, you don't receive as much attenuation. So that's what this is what our notch filter will look like, or what we shaped our notch filter to look like. So once we have that, we convert to the time domain using IFFT again, just like normal, and we window the response just like how we window response or window all the other time domain responses to obtain the FIR coefficients. So then I just quickly plotted the time response, and then here's what the window time response looks like. This FIR frequency response is me taking the windowed response and observing the frequency domain to see what our actual frequency response looks like. So this is what our actual frequency response looks like. It doesn't attenuate all the way down to 0 at 500. Notice how at 500 it's still 0.02, 0.025, 0.0236. So it's not fully attenuated, but it is heavily attenuated at the sampling frequency. And then as you move away from the notch frequency, the attenuation decreases. And so then I plot that. And so this FIR dump is the same function that's used to take those coefficients from the time response, not the frequency response, but from the windowed time response, because we want the time domain values as our coefficients. So it takes the time domain from the extractor response and turns those into coefficients that we'll use in our C program. I also include the simulate down here to simulate it just like how we simulated filters in Project 2 by feeding them one sample at a time. So this time for each time sample. And so we can test the input with a signal. I'm testing out the notch frequency. So if we input a signal at the notch frequency, it should be attenuated to about 0, not exactly 0 because the limited number of taps. And I've also tested it with Gaussian noise to see the general shape of the filter. And so then this is the exact same thing as what you'd see in C code. You'd set the first index equal to the input, you'd form the dot product, you would store the outputs. Now, the only thing different here is that since I'm using MATLAB, and MATLAB has a lot more resources on the DSP board, I went ahead and implemented a shift register instead of a circular buffer. So this is going to be a shift register, but other than that, it's relatively the same. And then we plot the outputs. So if we want to see the simulation outputs, notice that the output's been attenuated. The output here has been attenuated based on because it's at the notch frequency. And if we look at the noise, generally Gaussian noise contains all frequencies, but when you apply the filter, it becomes shaped to match the shape of the filter. So at 500, it's relatively low. All right, so with all these things in mind, let's move on after, because down here, this is just the same function that we use to take those coefficients and store them in a C file. And this is the file location, and all this is the same as before. So I'm going to quickly run this a second time just to make sure that I've updated my coefficients. Oh, let me run that again. Just in here and run that. So we've updated our coefficients. Now the notch frequency is at 500. So if we go into Code Composer, so right now I have the notch filter project open. So again, since we're just implementing an FIR filter, the code in the ISR is the same. It still uses the same coefficient.h header, but the values in here are different. That's the only difference, because we're still going to use the same circle or circle buffer code as we've used for all the other FIR circle buffers. And so none of this has changed. The only thing that has changed is the coefficients that we obtained, and these coefficients are now to form the notch filter. So then we make sure our DSP configuration, we make sure the sample frequency is about 8 kilohertz, just like in MATLAB. And so then we're ready to debug. So we go ahead and we debug, and this downloads it onto the board. So that means we're ready to go. All right. So we can first test at a frequency above the sampling, above the notch frequency, so at 1000. You can hear it. It's slightly attenuated, because if we look at what our actual frequency response looks like, oh wait, maybe it's not attenuated. How much attenuation should we expect to see? Oh, we should expect no real attenuation, since it looks like at 1000, it looks approximately about at 1. So this is what a normal signal will sound like. Let me increase the volume here. So this is what a normal non-attenuated signal will sound like. And if I take a lower tone, let's say it's 300. So 300, here's the 300 tone. The 300 tones, how much attenuation should the 300 tone have? Let's see. So the 300 tone should have some minor attenuation, but it should still be audible, which is what we're hearing right now. But if we take the 500 frequency tone, this one should be cut out because of the notch. So notice how it sounds completely attenuated, but if I turn up the volume to max and put it really close, you might be able to hear it, but it's basically attenuated to be really quiet. So this is at max volume. So right now it's been attenuated by a lot, just like how the notch filter should attenuate the notch filter, or attenuate the notch frequency by a bunch. Compared to the sine, or compared to higher frequencies around, above and below the notch frequency that are not as attenuated. So this is not attenuated. And then if we go to 300, like before, you see that this is not attenuated either. So with this, we can see that the notch filter is working exactly how we programmed it. So notice that it's not attenuated completely to 0 here, because the number of taps that we have is finite. So it's never going to be exactly going to match the shaped response, but it works relatively close to the notch filter. And so this basically concludes our notch filter design. So even though we don't actually know what the transfer function or of what the notch filter is, FIR filter design is very flexible and allows you to design filters even if you don't know certain characteristics of the filter, as long as you can shape the frequency response. So like I said earlier, my frequency response is shaped by an exponential, which is why I have those curves downwards and upwards right there. And this is how I created my notch filter. So this pretty much concludes the notch filter demonstration. In the next video, we're going to talk about the flanging and chorus effects. Actually, I may make flanging and chorus together as separate. I haven't decided.